Good afternoon, everyone. Welcome to week 2 of the NPTEL course on Coherence and Quantum Entanglement, which is being taught by Professor Anand Kumar Jha of IIT Kanpur. For those of you who are joining for the first time, I am Radhika Prasad, a PhD student at IIT Kanpur, working under the supervision of the course instructor himself, Professor Anand Kumar Jha. So, as we have discussed earlier, this is a 12-week long course, and every week there will be one short quiz of 10 questions, and we will also conduct these live problem solving sessions where the aim is to solve some problems and questions which will help you in solving the quiz problems. So we saw some questions last week, and now continuing in that, we will look at some more questions this week. And also the YouTube channel is there for these live problem solving sessions. So if you happen to miss any of these sessions, you can go ahead to the YouTube channel. The YouTube channel is under my name, Radhika Prasad, and you can go to that channel and rewatch the video as many times as you like. Okay, so let us now get started with the week 2 questions. This is a question and it has multiple subparts to it. So let me first read out the question for all of you. This is problem 1, and it says consider the following random process zt equals summation an e to the power minus I omega n t, where we are adding n terms, in which omega n are fixed frequencies and an are random variables. Then we have 5 parts to this question. The first part says, what do you understand by a stationary random process, and what are the conditions for a process to be stationary, at least in the wide sense? This is a very definition type question. Next part is, what are the conditions that ensures that zt is at least a wide sense stationary process? Part C. Next, check whether or not the above process is ergodic. For that, you have to check if the ergodicity condition, which is given as follows, limit tau tending to infinity of mod of gamma tau minus expectation of z mod squared tends to 0 is satisfied. And we are given a hint that we can use omega n equals omega naught plus n delta omega. Assuming, the next part says, assuming mod an squared equals 1 over n, then we are supposed to plot this term for which is essential for the ergodicity condition, that is mod of gamma tau minus expectation z mod squared, as a function of tau for tau ranging from minus 1000 to 1000, and we are given some conditions on n and delta omega. For n equal to 100, delta omega equal to 0.1, and for n equal to 100 and delta omega equals 0.0001. Comment on the main difference between these two cases. Part E says, comment on what happens to the ergodicity condition in situation in which delta omega tends to 0 and n tends to infinity in a way that n delta omega stays finite. So in this, as you can see, part D is about plotting the function, and plotting the function which is required in testing the ergodicity condition. And for plotting, we will be using Mathematica simulations. So for that, we will head over to the Mathematica environment. And all the other questions are like pen and paper derivation questions, so we will do that. First, take about a moment to read the question again and try to understand what the question is asking. Then try to get started on your own for like a few minutes, and then I will start and we will discuss the solution. So try to see if you can understand what this question is asking and if you can start attempting this problem. It's a good habit to always, try the question before the instructor solves it for you. Okay, so now that you would have at least got some understanding of what the question is, and maybe you have tried writing down some steps, let us look at the solution. Okay, wait, what is wrong with my pen? Yeah. So part A is a definition type question. It asks you, what do you understand by a stationary random process, and what are the conditions for a process to be stationary, at least in the wide sense. So a stationary process, let me define it for you. So a stationary process is one in which all the correlation functions correlation functions of the given random process, the random variable, are independent of time. And wide sense stationarity would be that means mean and 2-point correlation function, 2-time correlation function. So these should be independent of time. So stationary process means that all the correlation functions should be independent of time. The first order, second order, third order, all the correlation functions. Whereas stationary in the wide sense only requires the mean and the 2-time correlation function to be independent of time. The higher order correlation functions are not considered in the wide sense stationarity. That was for part A. Let us look at part B. So part B says, what are the conditions that ensures that the given random process ZT is at least a wide sense stationary process? So let us look at that. So what is mean? You would have seen this in the previous week as well. So expectation value is the mean. So an is a random variable, so we need this mean can be translated to an. So this becomes follows. The mean is written now like this. So this is mean. And now we also need to consider the correlation function. So correlation function is gamma t comma t minus tau, 2-time correlation function, which is given as z star t z t minus tau. Expectation of that. I'm just simplifying it. The expectation can be transferred to these random variables. Summation comes out of it. So this is the mean and the correlation function. Now for White's stationarity, we want the mean and the two-time correlation function to be independent of time. And how we will get that? We will get that so for White's stationarity, the mean should be independent of time. That means expectation of an should be equal to 0. And we also want an star am from the two-time correlation function to be delta mn expectation of mod an squared. So when m is not equal to n, delta mn equals 0, and when m equals n, delta mn equals 1. And why we are selecting this is because in the mean, or in the expression for the mean, we have this time dependent term. So the only way that this process can be independent of time is when this term is 0. And similarly, in the correlation function, we have this term right here which depends on time, because tau is a fixed number. Tau is a fixed number over here, so tau is independent of time. And this exponential it omega n minus omega m is the time dependent term. So the coefficient of that is this expectation an star am. And we clearly see that when n equals m, then omega n minus omega m will become 0, and exponential 0 is just 1. So when n equals m, we can have a finite number for expectation an star am. Whereas when n is not equal to m, then we want this exponential term to vanish, and for that this an star am needs to be equal to 0. So for those of you who are not aware of this delta function, sorry, let me write down. So this delta function over here is the Kronecker delta function, which means that delta ij equals 0 if I not equals to j, and it equals 1 if I is equal to j. So this completes part B. The next part is to check for Godicity condition. Let us start with that. I hope there are no questions up until now. If there is any question, please feel free to either unmute yourself and ask, or you could even put it up in the chat box, or you could even put it up as a comment on the YouTube video. Okay, let me see. Okay, so it seems we can proceed ahead. So let us see. So gamma tau, let us write that. We get it from this 2-time correlation function. The time independent version for wide sense stationary. So this is nothing but, so this an star am we saw needs to be delta mn expectation of mod an squared. So that's what I'm writing over here now. Mod an square exponential I omega n tau. Now the ergodicity condition, let me rewrite the ergodicity condition. So that's the ergodicity condition. Now let us see what let us rewrite our expression for z. So this means that at t equal to 0, and this we saw earlier needs to be 0 for wide sense stationarity. So why we consider t equals 0? Because for wide sense stationarity, the mean should be independent of time. So whether it is at t equal to 0 or t equal to 1 hour, the expectation value or the mean should remain the same. So this term goes to 0. So that means we need to now check. Therefore, we need to simply check if the following limit tau tends to infinity of mod of gamma tau, this should go to 0. And we are given that we can take omega n equals omega naught plus n delta omega. So putting in this gives me gamma tau omega n is now nothing but omega naught plus n delta omega. I'll take omega naught tau outside because it is independent of n. I'm just opening up the summation. So this is the expression for gamma tau. Now let us consider a few simple cases first. So let us first consider a few simple cases. So first case, let us take n equals 1. So that simply gives me gamma tau mod squared equals mod E1 squared. Why? Because these exponential terms cancel out when taking the mod. So just to remind you, mod of alpha is nothing but alpha star alpha. Oh sorry, mod of alpha squared is alpha star alpha, where alpha is a complex number. So this is for n equals 1. Let us now look at n equal to 2. These are just some simple cases that we are first trying out before going to the general case. Okay, let me rewrite it again. I don't know what's happening. Why is my eraser not working? This and then the complex conjugate of this. I'm just simplifying it, opening up the brackets. So this definitely cancels out with this. And further we can combine these two exponential terms to give a cosine term. So further simplifying, And exponential minus I delta omega tau plus exponential I delta omega tau is nothing but 2 cosine delta omega tau. Now we can clearly see from this expression that as tau tends to infinity, what we have is gamma tau mod squared. This does not go to 0. Why? Because we have this cosine delta omega term, this cosine delta omega tau term. Because of this, it does not go to 0. Why? Because since the cosine delta omega tau term is an oscillatory function, what do I mean by oscillatory function? It means it keeps oscillating between plus 1 and minus 1. So if I draw cosine, the plot for a cosine function, a cosine function will keep oscillating between plus 1 and minus 1. No matter what your tau is. So if this is my tau, this is cosine delta omega tau, and this value over here is plus 1, this value over here is minus 1. So it will keep oscillating between plus 1 and minus 1, and it will never tend to 0, no matter how big your value of tau is. So using this special case itself, we can see that the process is not ergodic. Why? Because we wanted to check for a general case, but the system is not ergodic even for the special case of n equal to 2. Then that means that the system is definitely not ergodic. So let me just write down what I said. So we wanted to check for a general case. But if the given system is not ergodic, even for the special case of n equal to 2, then the given system will definitely not be ergodic. So even with the special case, we can see that the system is not ergodic. But let us, for the sake of completeness, check with the general case as well. So the general case tau, let us write down once again. So gamma of tau is given as this. Just rewriting the expression. So now let us look at mod gamma tau squared. Now this will have n squared terms. Why? Because we saw even with the special case, so n equal to 1, 1 squared is 1 term. N equal to 2, 2 squared is 4 terms. You can see 1, 2, 3 and 4, 1, 2, 3 and 4 over here in this line. Just expanding, okay? So this is coming because you have n terms in gamma star t, n gamma star tau, n terms in gamma tau. So n cross n, that will give you simply n squared terms. So this is n terms here. So gamma star gamma tau gives you n into n, which is n squared terms. Now out of these n squared terms, you will have n terms of the form mod an to the power 4. As you saw here, for n equal to 1, we had one term with mod a1. Sorry, this should have been to the power 4. My mistake. Sorry, let me recorrect myself. So I've just corrected myself because it is gamma star gamma. So as a result, a1 to the power 4. And for n equal to 2, you can see you have two such terms, a1 to the power 4, a2 to the power 4. So n terms will be of the form an to the power 4, mod an to the power 4. And the remaining terms will be these cross terms. Cross terms means these terms which contain this exponential terms. So the remaining terms will be the cross terms. So n terms of the form an to the power 4 and the remaining n squared minus n cross terms. Cross terms meaning which contain the exponential terms. Now, as you can see that these cross terms are complex conjugates of each other. So here we saw exponential minus I delta omega tau and exponential I delta omega tau. These are complex conjugates of each other which can be combined to give us the cosine term. So, out of these n squared minus n terms, n squared minus n cross terms, what we have is n squared minus n by 2 distinct terms and the remaining n squared minus n by 2 complex conjugates. And what we can do is we can combine these sorry, let me redo. What we can do is we can basically combine these terms to give cosine like terms. And let me just write down what these terms will look like. So these terms are going to look like as follows. They will look like, so I'm writing this cross terms here. These cross terms, so they will look like mod ak squared mod aj squared and this we will combine and it will give us cosine. Now again we see that this is a cosine term, so it is oscillatory in nature, so it will not tend to 0. So finally we can conclude that as tau tends to infinity, gamma tau mod square does not tend to 0. So this means that the system is not ergodic. I hope this is clear. There were a lot of algebraic steps involved over here, so take about a minute to digest this. If you have any questions, please feel free to ask. Just try to understand what we have just now seen. Okay, so it seems okay. Let me. Oh, there is one question. Some people, someone is asking about how I am concluding after getting this cosine term that it will not tend to 0. Okay, so good question. So the reason why I'm saying this will not tend to 0 is because, see, this is the plot of the cosine function. It is 0 at some point, but it does not tend to 0. You see that it very evenly keeps on oscillating between +1 and -1. When I say that a function tends to 0, what it would mean is, let me redraw a function which will tend to 0. Let me just come up with some function. So if I were to draw a function like this, something like this. So this function tends to 0. You see, it is oscillating, but the amplitude is continuously decreasing. See, this amplitude is continuously decreasing. So this function slowly tends to 0 as tau increases. An example of this function, such a function would be exponential minus tau cos delta omega tau, let us say, something like this. So something like this will be tending to 0 as tau tends to infinity. But simply cosine delta omega tau will not tend to 0. So I hope I have made myself clear. I think we can proceed further now. The next part is actually on plotting. So we are given one expression for mod n square, and we are supposed to make a plot and make a plot with varying values of delta omega. So we will use Mathematica for this. Let me write down. So part D is basically plots for constant n and variable delta omega. And what are we actually plotting? We are plotting this mod gamma tau squared, and since this goes to 0, it is simply mod gamma tau squared. Mod gamma tau squared is what we are plotting, and we will use Mathematica simulations. And what we will see is that as delta omega increases, the width and revival period, which is the periodicity for this function gamma tau mod squared, will decrease. Let us now head over to Mathematica and see the simulations for ourselves. Let me open up my Mathematica screen. The Mathematica programming environment. Okay, so I hope the screen is visible. Okay, so let us just see the plots. So here I am in my Mathematica window. Yeah, this where is my cursor? Okay, here. So this is my Mathematica window, Mathematica programming window, where I have already written down the code for you to generate the plots, and we see different plots over here. So basically what I'm doing is I'm trying to plot a mod of gamma. So the expression of gamma I have given over here. So if you just go back and check what we have derived as the expression for gamma. So by definition, gamma is nothing but mod an squared times exponential of I omega n tau. So that is what I have over here, and an squared, mod an squared, we are given in our example as 1 over n squared, which is fixed. So it's a fixed number, and then we have exponential I omega n tau, and omega n we have is basically n delta omega. Why? Because omega n is omega naught plus n delta omega, and when omega naught comes out and in gamma squared you do not get the omega naught term. So that is what I am plotting over here. This was what the question was. Wait, let me just go back and check if all the values and expressions that I have written are correct. Yeah, so it seems, just give me a second. So you, all of you, also please check. I'm also going back to my notes and checking if I have written down the expression correctly or not. Okay, one error I have made is we are given that mod an squared equals 1 over n and not 1 over n squared as I have written over here. So let me correct that. It is 1 over n, and also I'm supposed to plot mod gamma squared and not just mod gamma. Oh no, I am supposed to plot mod gamma only, so that is fine. But en squared is 1 over n and not 1 over n squared. So let me just, okay, something is going wrong. Okay, let me remove this plot range. Okay, yeah, so plot range should be from 0 to 1, because 1 over n squared I changed to 1 over n now. Okay, that's better. So this is for n equal to 100 and delta omega equal to 0.0001. Let me fix it for other examples as well. This is for different omega, but I need to change my mod an squared, and I need to change this plot range as well. So why it is going to 1? Because mod an squared is 1 over n, which is 1 over 100, and then we are adding it 100 times. So 1 over 100 times 100, that will give you 1. So that's that. As you see that the form of the function, the structure does not really change much, because that was just a constant. Whether I call it 1 over n squared or 1 over n, that's still a constant. So the feature remains similar. Okay, so let's start from the beginning. So n is constant, which is 100. And in all these 4 plots, what is changing is delta omega. And how is it changing? So we are starting with a very small delta omega, and we are slowly increasing the value of delta omega. And we can clearly see that as we are increasing the value of delta omega, the width of this gamma plot decreases. So here the width is about, let's say, from about minus 500 to plus 500 of the central peak, and here maybe it's about from minus 80 to plus 80, if so to say. So how do we find width? We basically look at full width at half maximum. So I'm just looking by eye estimation approximately. So you see that if delta omega increases, then the width decreases. Now we increase delta omega even more, and we see that the width has decreased even more. Now it is almost like a very sharp peak. And we also see this periodicity. This periodicity is coming because of that cosine like term due to the cross terms. So this periodicity is also decreasing. And how we see the periodicity decreasing? Well, if we increase delta omega further, we see extremely sharp peaks, and then we see that the periodicity has decreased. Uh, there is some numerical issues happening with these peaks. These peaks all will go up to value 1, all of these. So that's just some numerics which is happening over here. Let me try and increase the number of points and see if, see, now if I have more points, you see that the numerics basically tries to correct itself and all the peaks are at least becoming closer to 1. If I take even more points, oh, I'm not sure, I think my computer will, now you see, now I have many more points. I have like 500 points, and you see each of these peaks goes to 1. So, and you see that the peak is very sharp now and the periodicity has decreased. So from these 4 plots, you see that if n is kept constant and if delta omega increases, then the plot of mod gamma, in the plot of mod gamma, the width of the central peak decreases and also the periodicity decreases. Periodicity, by periodicity I mean the time period. Then here I have actually made a manipulate plot. Let me correct it over here. It should be 1 over num. Okay, let me, oh, something has gone wrong. Let me put num squared once again, and something funny with the range is happening. Okay, yeah, now I think it is fine. Let me rerun it. So yeah, so here is a manipulate plot. So what you can do is just play around with the number of terms and also delta omega. So as we change number of terms and delta omega, you can see the features. So right now only one term. So if it is only one term, it will remain flat, and then as delta omega is increasing, you see how the plot is changing. So let's now come back. Sorry, not one term. This is sum of 10 terms. The 0 is not visible over here somehow. So 10, 50, 100 and 150. So 10 terms, and if I am increasing my delta omega, you see slowly that the width is decreasing. I can increase the range further, and then you will see the feature even more clearly. Now if I keep delta omega constant, and if I increase the number of terms, you see again, if delta omega is constant and if the number of terms is increasing, then also the width is increasing. So delta omega is constant, number of terms is increasing, then also the width is decreasing. So whether you keep delta omega constant and increase the number of terms, or you keep the number of terms constant and increase delta omega, in both the cases your width of the central peak decreases. See, I am keeping delta omega constant and increasing n, then also the width is decreasing, and also periodicity will. So periodicity is same, only the width is changing. So you see that if I keep delta omega constant and if I keep changing my n number of terms, then only the width of the peak is changing, whereas the periodicity remains same. So periodicity is governed by the number of terms in the summation, and if I change the number of terms, periodicity is governed by delta omega, pardon me. So if I'm changing the number of terms, if I'm increasing the number of terms, the width of the peak is decreasing, but periodicity is same. And if I keep n constant and if I change delta omega, then width is also changing and periodicity is also changing. See, width is changing and periodicity is also changing. So periodicity is governed solely by delta omega, whereas the width of the peak can be controlled either by changing the number of terms in the summation or by changing delta omega. In both the cases, if you increase number of terms or if you increase delta omega, the width of the peak will decrease. So this was about these plots and simulations. Let us now get back to our question. Okay, so now let us come back. As you saw in the Mathematica plots, as delta W increases, the width and the revival period for the function gamma tau mod squared actually decreased. So this is what we saw using these Mathematica simulations. Let us now come to the last part of the first question. So this says that comment on what happens to the ergodicity condition in the situation in which delta omega tends to 0 and n tends to infinity in a way that n delta omega stays finite. So what we have is n tends to infinity and delta omega tends to 0 such that n delta omega is finite. So let us write down the expression for gamma tau once again. Now with n tending to infinity and delta omega tending to 0, what we have is that the summation will tend to an integral. So what we will get is basically that gamma tau will be equal to, instead of a summation, now we will have an integral. this is what will happen. So this is the simple situation where where the summation goes to an integral. This is what happens. So you can check out the Riemann. Oh, sorry, I need to go back to my pen. You can check out, let me change the color, Riemann sum and integrals, because that is the condition for a summation to go to an integral, or the other way around, an integral being approximated by a summation. So this brings us to the end of problem 1. There were 5 parts to this problem, and we have solved each of these parts, and we even saw some plots in Mathematica, some simulations, to get a better understanding of exactly what is happening. And now we can move over to the next question, which is problem 2. Before that, please take about a few minutes to check whether you have fully understood this question or not. If you have some questions, please post in the chat box. Okay, someone is asking what is the difference between this Kronecker delta and Dirac delta function. The answer is there isn't much of a difference. Dirac delta function is just the continuous version of the Kronecker delta function. So in Dirac delta function, let me write down, it's just the continuous version. Dirac delta function is defined as follows. uh, so this definition is that this is defined as follows. It is infinity for x equals 0 and 0 for x not equals 0, and it's also defined um, like in the integral a to b. This will be equal to 1 if 0 belongs to the interval a comma b, and it is 0 if 0 is not in the interval a comma b. So that is the continuous version for the Kronecker delta function, which is the Dirac delta function. Okay, so this finally brings us to the end of problem 1. Next up we have problem 2, which has two parts this time. So let me read the problem first for you. The problem says let V R comma T be a real field, and let's assume that it can be represented in terms of its Fourier components as follows. So we write this capital V as integral of small v e to the power minus I omega t d omega. This is just the Fourier form, which is written as a Fourier transform, and then the limits of the integral for a Fourier transform is minus infinity to plus infinity. So we are simply splitting it up into two parts, minus infinity to 0 and 0 to infinity. And this is basically, these terms are basically complex conjugates of each other. Now this VRT is called the complex analytic signal corresponding to the real variable, and in coherence theory the time averaged intensity IR of a field at position R is proportional to the expectation of V star V. And in the classical electromagnetic theory we have I, which is given as simply V expectation of V squared instead of V star V. So now we are supposed to show some expressions concerning this complex analytic signal and the real field and the complex conjugates and the Fourier components. So this so we are just supposed to prove this statement, which involves all these: the real field over here, the complex analytic signal part, the V star V, the Fourier components over here and here. And then finally we are supposed to see how the intensities are related. Okay, so take about a few minutes to read the question once again for yourself and try to understand what the question is about. It's always a good practice that before you actually attempt a question, you read it a few times to actually understand what is required in the given question. Okay, so now let us look at the solution. Let us look at part A first. Let us start. Let me first write down this complex analytic signal. So the real field that we have is written in the Fourier component form. And we can split it up into two parts, minus infinity to 0 and then 0 to infinity. And this is written in the complex analytic signal form as follows, where this first term, this negative part, this is V star, and then this right here is this And also let me write down the intensity what is given to us. This, and for the real electro fields in the electromagnetic theory, and this expectation or the averaging is over the period of time. Now let us start part A. Let us start with the left hand side. So let us now do some algebra and simplify. So all that I have done is represented this real field in a Fourier component form as we are given over here, and then taken a square of that. Square of that means you multiply it with another integral. So this gives us two integrals over d omega and d omega prime, and then an integral over time dt. Now, as I had defined this Dirac delta function, someone had asked earlier, we will make use of this Dirac delta function, and another definition, another way to represent this Dirac delta function is as follows. This is another form in which you represent the Dirac delta function. So we will make use of that over here. So this will become 2 pi delta omega plus omega prime. Why? Because let me rewrite it again over here. How we get this? Because this picks up value only when omega equals minus omega prime. So from here we will get and y. Let me also rewrite that clearly over here. So what we had was, we had this integral. This integral basically gives me the following, because this delta function picks out the value for which the argument is 0, as we saw earlier in the definition. This integral gives the value 1 only when x equal to 0 is available, is present in the limit. And also when you have a function integral over the entire limit, this will give you, pick out the value at f equal to 0 for x equals to 0. So these are the properties of the Dirac delta function. Using that, we come to this line, this expression over here. Now v minus omega is actually equals to v star omega. So this gives us so how we, sorry, I need to write down r also. How we get this is because, let us see. So what we have is this expression, which is the definition for the Fourier. Now let us look at the complex conjugate. So let us now look at the complex conjugate. Now in this integral, let us take omega goes to minus omega. So this will give us, the limits of the integral will flip over. And now this d minus omega will be minus d omega. So again the limits of the integral will flip once again. Now, since this is a real field, the complex conjugate will be equal to the field itself. So, what we have is that the given field is equal to the following. So these terms are equal. That means V star r minus omega equals V r omega, or in other words V star r omega equals V r minus omega, if we simply put omega goes to minus omega. So finally we are able to prove the first part of the expression. So one of the parts that we have so this part we have shown that this is the equation 1. Now let us look at this term over here. So let us look at this term. This comes from here, these terms over here. So this, sorry, this is the first term, which is V star t, and this is the second term, which is Vt. Now let us put omega goes to minus omega in the first term. Now again this will give us the Dirac delta function. And this is nothing but, as we showed, this is V star R omega. Now integral over omega prime of this delta omega minus omega prime will pick out the value omega equals omega prime. So this will give us a single integral now. Which is 2 pi can be taken out. Which is why we get this is because we know that the integral of an even function from minus infinity to infinity is 2 times the integral from 0 to infinity. And definitely mod squared is an even function. Mod squared is even function. So from this we get this, and that means if we multiply 2 to both the sides, we have 2 . So we get this. Let us call it equation number 2. So this has actually completed this part of the equation. And we see that from 1 and 2 that these are identical, equal. Now let us look at the last term. So from this to this it is pretty straightforward, because as I said, integral of minus infinity to infinity of an even function is 2 times the integral 0 to infinity of that. But let me just show it once again explicitly. just doing simple algebra. Let me call this equation number 3. So this is actually the third part over here. Now when we put together 1, 2 and 3, we get the desired result, that is this gives equation 4, which is the final desired result. Since there was a lot of steps involved in getting to this expression, because there were like 4 terms over here, and it required simple but maybe too many algebraic steps. So take about a few minutes to just recapitulate what we have actually done over here. Okay, so now let us move to the last part. This is very simple for intensities. Now from this equation 4 over here, so this gives us that the intensities are also proportional, and we know why, because this part is nothing but integral of the following expectation value, and this from 4 we have seen is 2 times the following, and this part is nothing but the expectation of V star V. So from that we finally get the desired result. So this brings us to the end of week 2. Again, we solved very subjective questions. The quiz is all the quizzes will comprise of MCQ questions, but each of those MCQ questions, if you notice, basically require you to derive some expressions, and that's why we are solving these subjective problems in these live problem solving sessions, so that you understand how to really work out the maths, and once you understand this, then you will be able to solve any kind of MCQ type questions. So just take a few minutes to recapitulate all that we have done in this week 2. We will meet again next Saturday at 3 p.m. for discussing week 3.